evaluate the surface integral using a parametric description of the surface. And here we're given the function f of x, y, z is equal to 2x squared plus 2y squared, where the surface S is the hemisphere, defined as x squared plus y squared plus z squared equals 9, where z is greater than or equal to 0. So let's simply get started here by sketching this surface. So we have our z-axis, we have the x-axis, and we have the y-axis. And we know that this is a hemisphere, so we'll try our best here to sketch this picture. Or sometimes I like to start with a whole circle, and then we just want to think about half of this, the hemisphere that's above the XY plane. So we're going to erase the bottom half here. And as always, this is not art class, so just try your best and label. So this is the hemisphere that we are thinking about. So our region, or our surface, S. And looking at what we're given here, this hemisphere has a radius of 3. So we'll indicate this on our sketch. And it's bounded below, or the hemisphere itself is above our XY plane. So we can use this sketch here to go ahead and define the bounds in spherical coordinates. So since we know our sphere, or our hemisphere, has a radius of 3, we can say that the bounds on rho, our radius, is greater than or equal to 0, less than or equal to 3. Now, since we know our hemisphere is above the XY plane, we can see that the bounds on phi, the angle from the positive z-axis, is greater than or equal to 0, less than or equal to pi by 2. And then we can see here, looking at the cross section in the XY plane, it's a full circle. So we can say that the bounds on theta is greater than or equal to 0, less than or equal to 2 pi. So these bounds in our spherical coordinates are going to be important as we proceed in finding the parametric representation for this hemisphere in terms of u and v. So to get us started, I'm going to let u be phi, and we're going to let v be theta. We need a little bit more room. So here we know what rho is. So since rho is equal to 3, we can rewrite our conversion formulas as follows. We know that x is defined as rho times sine of phi times cosine of theta. So we can say that x is equal to 3 times sine of phi cosine of theta. We know that our conversion formula for y is rho times sine of phi times sine of theta. So we can write this as 3 sine of phi sine of theta. And last but not least, we know that z is defined as rho times cosine of phi. So we can say that this is 3 cosine of phi. And so we'll now use these to parameterize each component. So we have the parametric representation of x in terms of u and v is going to be 3 sine of u cosine of v. We have the parametric representation of y in terms of u and v is equal to 3 sine of u times sine of v. And last but not least, we have the parametric representation of z in terms of u and v is equal to 3 times cosine of u. And so we are able now to go ahead and conclude that the parametric representation, vector r of uv, for this hemisphere is defined as 3. So actually notice here, we've got a common 3 in each one of these components. So for simplicity in computation, let's pull that 3 out in front. So we have 3 multiplied by the vector with components sine of u, cosine of v, sine of u, sine of v, and last but not least, cosine of u. And this is where, since u is representing phi, we know that phi is going to be, u is going to be greater than or equal to 0, less than or equal to pi over 2, and since v is representing theta, we know that v is greater than or equal to 0, less than or equal to 2 pi. And so here is our parametric representation for our hemisphere. And we're ready now to go ahead and use this to calculate the magnitude of the cross product of the tangent vectors with respect to u and v, as well as rewrite the function. So we'll start here by calculating the magnitude of the cross product of the tangent vectors of u and v. So to find the tangent vector in the u direction, we need to take the partial derivative of vector r with respect to u. So this is going to leave us with 3 multiplied by cosine of u times cosine of v. We then have cosine of u times sine of v. And our last component, the partial derivative of cosine with respect to u, leaves us with minus sine of u. So similarly, to find the tangent vector in the v direction, we take the partial derivative of vector r with respect to v. So we have 3 multiplied by minus sine of u times sine of v. We then have sine of u multiplied by cosine of v. And then the partial derivative of cosine of u goes to 0. And so we're ready now to go ahead and take the cross product of the tangent vector in the u direction, cross with the tangent vector in the v direction. And just be careful here when you plug these in. Don't forget about the scalars in the front, those 3's. So we have 3 times 3. And I'm going to write this actually right below because we have a big computation here. So don't be scared. Just take your time. So we have 9, and we're applying the cross product here. So this is 0 minus minus, so plus sine of u squared times cosine of v. And this is all multiplied by I hat minus, we have 0. So we have a negative times a negative times a negative. So we have minus, it's going to be sine of u squared times sine of v j hat plus, and last but not least, we have cosine of u, sine of u times cosine of v squared. So cosine of u, sine of u times cosine of v squared minus, so we have a negative times a negative, so that'll be plus sine of u times cosine of u times sine of v squared. We still need a little bit more room. So we have cosine of u, sine of u, sine of v squared. And don't forget that is a square. That's all multiplied by k hat. So I should have made it a little bit bigger to begin with. All right. So we have some nice simplification here. So we can rewrite this as 9 multiplied by sine squared of u cosine of v I hat. This will become plus sine squared of u times sine of v j hat. And then looking at this last term here, notice that we have a greatest common factor of cosine of u, sine of u. So I'm going to write this right above. If we were to factor that cosine of u, sine of u out in the front, then what's left over is cosine squared of v plus sine squared of v, k hat. And we see Pythagorean's identity, so that all cancels or is equal to 1, which leaves us with plus cosine of u, sine of u, k hat. Phew! So we did it. The worst is behind us. So now we can go ahead and compute the magnitude. And actually, before we even do that, we're looking at this vector here, and we realize each term has a sine of u in common. So again, to help make our calculations a little bit easier, we're going to say that the tangent vector in the u direction crossed with the tangent vector in the v direction is going to be equal to 9, and I'm factoring out that common sine of u. And so we are left now with sine of u times cosine of v I hat plus sine of u times sine of v j hat plus cosine of u k hat. So now we can use this to go ahead and compute the magnitude. Woohoo! So again, just take your time. We're almost there. So we have the magnitude of the cross product of these two tangent vectors is equal to 9 times sine of u multiplied by the square root of sine of u squared times cosine of v squared plus sine of u squared times sine of v squared plus cosine of u squared. And so looking within this integrand here, and our first two terms, we notice that they have a sine of u squared in common. So let's pull that out. So this is equal to 9 times sine of u multiplied by the square root, and we're factoring that sine of u squared out in front of those first two terms. So that's multiplied by cosine of v squared plus sine of v squared, woohoo, plus cosine of u squared. And so we see Pythagorean's identity. So we know that that is equal to 1, which leaves us with 9 times sine of u multiplied by the square root of sine of u squared plus cosine of u squared, and we see Pythagorean's identity again. So we know that is also equal to 1, and so this leaves us with just 9 sine of u. So the magnitude of the cross product of our two tangent vectors is just 9 times sine of u. Woohoo! So now that we have the magnitude and we have our parameterization, the only thing left to do is to parameterize our given function. All right, so here we go, our final step. We need to parameterize the given function. So we were given the function f of x, y, z is equal to 2x squared plus 2y squared, and I just factored that 2 out in front. So looking at the parametric representation that we found at the beginning, we can see here that our x component in terms of u and v is equal to, so don't forget about that 3. We'd have to distribute it back through. So x is 3 times sine of u cosine of v. And we can see that our y component is equal to 3 sine of u sine of v. So I'm going to simply square them here. So x squared is equal to 9 times sine squared of u times cosine of v squared. And then if we square both sides of y, we get y squared is equal to 9 sine of u squared times sine of v squared. And taking the sum of x squared plus y squared, we end up with 9 sine of u squared times cosine of v squared plus 9 times sine of u squared times sine of v squared. And we've got a greatest common factor of 9 sine of u squared. And it's multiplied by what's left over, which is cosine of v squared plus sine of v squared, which we're delighted. We see Pythagorean's theorem again, we know is equal to 1. And so x squared plus y squared is 9 sine of u squared. So therefore our reparametrized function, so f parametrized in terms of u and v. So we have x of uv, y of uv, z of uv is equal to 2 multiplied by 9 times sine of u squared, which leaves us with 18 sine of u squared. Phew! So we have everything we need. We've got the parametrized function, and we've also got the magnitude of the cross product of our tangent vectors, as well as the bounds on u and v. And so we're ready to set up that surface integral. So here we go. And we'll give ourselves more room after we rewrite this. So we want to set up the surface integral for this parametric description. So we have the surface integral over that surface S of the function in terms of x, y, and z, which we would integrate with respect to S. And now plugging in everything we just found, we have the integral from 0 to 2 pi, the integral from 0 to pi by 2 of the parametrized function 18 sine squared of u multiplied by the magnitude of the cross product of our tangent vectors 9 sine of u, and this is du dv. So we are ready now to start evaluating. And so let's see, we can rewrite this. 18 times 9 gives us 162 multiplied by the integral from 0 to 2 pi, the integral from 0 to pi over 2. And what I'm going to do here, we could combine this to get sine of u cubed, but then we would need to expand it back out. So in order to integrate this, I'm going to rewrite sine squared of u as 1 minus cosine of u squared times sine of u, and this is du dv. And so by rewriting it like this, now when we evaluate that inner integral, it's all set up for us and ready to go. So this is 162 times the integral from 0 to pi over 2 of 1 minus cosine of u squared multiplied by sine of u du. And so applying a little u substitution here, I'm going to let u be cosine of u, which gives us du. Oh, here, so too many u's instead of, so we'll use a w substitution. So we have dw du is minus sine of u, or we can think about this as minus dw all over sine of u is equal to du, and we can plug these in to our integrand. I'm also going to go ahead and change the bounds. So our bounds here are in terms of u. We know that u is an element of the closed interval from 0 to pi over 2, but we've now redefined the variable to be w. So we can say that w of 0, which is cosine of 0, which gives us 1, and then w of pi over 2, and cosine of pi over 2 goes to 0. So this says that w is an element of the closed interval from 1 to 0, which is certainly a contradiction, but we can easily fix these bounds with the order of integration property. So we can plug our substitutions in, and we have 162 times the integral from 1 to 0 of 1 minus w squared multiplied by sine of u, and then we've replaced our differential now with minus dw all over sine of u. So the sines of u cancel each other right out to 1. And when we apply the order of integration, the negative from the differential will cancel with the negative from that property. So we end up with 162 times the integral from 0 to 1 of 1 minus w squared dw. And so we can integrate this. We have 162 w minus w cubed all over 3. And we're ready to evaluate from 0 to 1. So we are left with 162 multiplied by 1 minus 1/3 and minus 0. So you have 162 multiplied by 2/3. And 3 is going to go into 162 54 times, which leaves us with 54 times 2 is 108. So that's our inner integral, and we'll plug this in to evaluate the outer integral, which is the integral from 0 to 2 pi of now 108 dv. And so this leaves us with 108 multiplied by 2 pi minus 0 for a beautiful final answer of 216 pi.